Hello and welcome to this final video covering section 8.2 of the notes. This should be a shorter video where we're going to state some theorems and some results and hopefully connect it to the last video. So this first theorem here, it says that if a series AN converges, then the limit of AN must be 0. Now if you need a translation of this, what it says is that if you're adding up infinitely many numbers and you get a finite value, then the numbers that you're adding up have to go to 0, right? There's no other way to get a finite value unless you're ultimately adding up very, very small numbers. That's what this is saying. Now the converse, that's what it's called, the converse is not true. Just because you add up numbers that get very small does not mean that the sum will automatically be finite, i.e. will automatically converge. And the prime example of that is the harmonic series. Notice the numbers I'm adding up, 1, 1/2, 1/3, 1/4, those numbers get small, they go to 0. But the series itself still diverges, that much we showed last time. So there's the distinction for you, right? This theorem only goes one way. It's like saying every square is a rectangle, but not every rectangle is a square, right? So every convergent series, the terms that I'm adding up must become small, but just because the terms that I'm adding up become small does not mean the series will be finite. And so for a counterexample of the converse, see the harmonic series. Now there is an operation you can do to this statement here called the contrapositive, which will give a true statement. So because this theorem is true, if when you add up infinitely many values and get a finite value, then the things you're adding up must become small. Well, if you flip the order and negate both statements, so notice here, if the limit of AN does not exist or the limit of AN is non-zero, then the series diverges, right? And so looking at this example here, we see that, well, the limit as n goes to infinity of n squared over 5n squared plus 4, so the limit of the things that I'm adding up, there's a few ways to show. You can use L'Hopital's rule a couple times, or use the fact that this is a degree 2 divided by degree 2 with n going to infinity. So you just take the ratio of the leading coefficients. Because the things that I'm adding up don't go to 0, I'm not going to get a finite value when I add them all up. Because eventually, think about it, you're just adding up roughly 1/5 over and over and over and over for large n values. And that's not convergent, right? So this diverges, which I'll write as DVGS, by what's known as the test for divergence. And there is no like one single test for convergence. This only works if you're trying to show a sequence diverges. So far, to show a sequence converges or something like that, you have to use either the fact that it's a geometric series, you have to use the fact that it's a telescoping series, or the fact that it's a harmonic series. Anything else, try to show it, argue through the test for divergence. Okay, and now we have one last cautionary note here. Once again, this says absolutely nothing if the numbers that I'm adding up go to 0, because harmonic series, right? Like that's always going to be the example I go to here, right? AN is 1 over n, which goes to 0, but when I add them all up, I get an infinite value, okay? All right, now some properties of series. If you know that you have two convergent series, then you can add them, multiply by a constant, everything you would expect to be able to do. So you can split up at a plus sign, split up at a minus sign, or factor out constants, okay? So looking here, we showed above, so let's write down what we know. The sum n equals 1 to infinity 1 over n plus 1, it converges and equals 1, right? And furthermore, we know the sum 1 over 2 to the n from n equals 1 to infinity also equals 1. And so what we have here is we have a sum of two convergent series, right? And so by this theorem here, I know that the sum 3 over n plus 1 plus 1 over 2 to the n, well, that is the sum. Because they're both convergent, I can split them up. So And now here I have a constant that I can factor out. So this is 3 sum n equals 1 to infinity 1 over n plus 1. This sum here we showed equals 1, and so does this one, so I get 3 times 1 plus 1, which is 4. Okay. So this series converges because it's essentially the sum of either a convergent series or a multiple of a convergent series. Okay. But these two series had to converge before I could do this. There are examples out there where such would not be the case. So they have to converge first, and then you can split them up individually. All right, that's it for this section. In the next video, we'll get into section 8.3, where we learn about some convergence tests.